Hello everyone. Welcome back to, well, I'm calling it Lecture 9, but it's really Lecture 8, Part 2. And this we're going to talk about closed feed water heaters. Closed feed water heaters are another tool engineers use to recycle the heat left over after during a fluid cycle. So, like before, I have a boiler up here, starting at step 1. Steam coming from the boiler into the high pressure turbine. Again, some of that steam is siphoned off, a Y amount, and 1 minus Y amount is left over to go through the turbine and through the condenser and etc. Well, what's the difference between a closed feed water heater and an open feed water heater? Well, a closed feed, unlike an open feed water heater, as you can see, these two flows do not mix. This closed feed water heater, the steam that is siphoned off from the high pressure turbine heats the water going into the boiler, preheats it, but these two never mix. Instead, this steam is sent off to the condenser to remix up with the water that is left after the low pressure turbine. As a result, so these two do not meet. But again, this heat exchange is between the steam and the water about to go into the boiler, and there is no heat exchange between the surroundings, only between the two fluids, and the fluids do not meet. That is the difference between a closed feed water heater and an open feed water heater. So, first things first, again, what we always do is we draw the TS diagram. Now I'm going from the boiler, I'm going to have P1. After the high pressure turbine, I'm going to have another pressure, I'm going to have lost some energy. And after the final turbine, I'm going to have a P2. And this pump pumps everything back up to P1. This valve is at P2 and ends at P3. There we go. Oh, this is labeled P2, P3. Alright. I hope you drew this out because we're not really going to be referencing it again. I have this exact same schematic on my desk, and that's how I will be creating the TS diagram. But you should be referencing the schematic, so make sure you have it drawn out. Alright, let's create our TS diagram. Okay, if this software decides to cooperate. I don't know why it's not. Come on. There we go. Now, you're going to notice this drawing is not going to be great. But, so, fair warning. Alright. P1. I'm sorry, P3. P2. P3. So P1, P2, P3. Sorry for the drawing. So, like I said up here, this is water freshly out of the TS. So water fresh out of the boiler, so it's steam. Right here, I'm at 1. So I flow down here going through the first high pressure turbine, state point 2. Some is siphoned off that way. The rest goes down through the low pressure turbine here at 1 minus Y. This here is labeled 5, so this is 5. Everything leaves the condenser at state point 6, so state point 6 I am liquid right here, saturated liquid, and I am pumped all the way up here to state point 7 to the pressure below that. Now this is why I was going to apologize for the drawing. This is a straight line here, but with line vertically up. In other words, I have to draw like this because you're going to find out in a second. So here I am going through the closed feed water heater, and I'm going to end at some point here. Don't know, say it's right about there. This is the water going through the closed feed water heater. And I'm going to go through a valve, which is isenthalpic, and this is how you draw it on a TS curve. So I'm ending here at state point 4, where I mix up with the rest of the water. So here is 1 minus y, this is y, and then it's all mixed together, continues condensing, and leaves here at the normal mass of state point 6, sent through the pump up here to state point 7, and is preheated up here at state point 8. So state point 8 is about right here, and then the rest of it is pumped through the heater back up to state point 1. Now, based off this drawing, T8 is less than T3. Alright, I know you can't see it with the drawing, but it is, because you can't heat water past the temperature of whatever you're pumping in. Like, so the water cannot be hotter than the steam that you're flowing through it. The best you can do is get them to be the same temperature. So T8 is less than or equal to T3. You will be told, or you'll be able to find out how to do it. And I'm going to show you how to find out. So now that my TS diagram is done, all that's left is to do control volume analysis. So let's do it. High pressure turbine. Previous video, I did the derivation for how to get all these different formulas for this stuff. So I'm just going to jump straight into giving you the work and heat transfer equations. So high pressure turbine, W is equal to m dot times H inlet minus H outlet. That's the work for the high pressure turbine. Low pressure turbine, I have the work, and I have here some of the mass was siphoned off, so I have 1 minus y going into the low pressure turbine. So it's going to be 1 minus y times the mass flow rate times enthalpy in minus enthalpy out. And now we get to the closed feed water heater. Alright, so it's a box. I have state point 2 coming in at y m dot, state point 3 going out at y m dot, state point 7 coming in at m dot, and state point 8 going out at m dot. So there's heat transfer between these two flows here. Heat will go this way and preheat the water, so you have to input less heat, less energy from the boiler. But there is no heat exchange between this control volume and the surroundings. So you analyze it exactly like you did with the open feed water heater. Sum m dot inlet H inlet is equal to sum m dot exit H exit. So plug them in. Y or m dot 2 H2 plus m dot 7 H7 is equal to m dot 3 H3 plus m dot 8 H8. So m dot 2 is y dot m dot. It's because I siphoned off some fraction y from the steam. So I get y m dot H2 plus, this is the full mass because everything recombined in the condenser, plus m dot H7 is equal to y m dot H3 plus m dot H8. M dots all cancel out. So you get y H2 plus H7 is equal to y H3 plus H8. And now you can solve for whatever you need to solve. If I'm going to be honest, Sometimes you need enthalpy 8, sometimes you need enthalpy 7, 2, 3. A lot of the time, you just need those changes in enthalpy to help you determine how much heat was exchanged between these two, or how much heat you need to add to the boiler. But that is going to be based off the parameters given to you by your professor and by your problem. So I'm not going to cover those because I just want to show you how to set up the equation and make sure you understand the process. If you know the process, doesn't matter what you're given, you can solve this problem. So next is the valve, isenthalpic, H3 equals H4. So now the condenser. H state point 5 coming in at 1 minus y m dot. State point 4 coming in at y m dot. And all the water is getting combined at leaving here at state point 6, which is just m dot. Well, heat is exchanged with the surroundings, so there you go, you're going to have Q. No moving parts, so work is equal to 0. So Q is equal to sum of the mass flow rates of the exit, enthalpy exit, minus sum of the mass flow rates of the inlet, enthalpy inlet. Q is equal to, well, so it'd be M6 H6 minus M4 H4 minus M dot 5 H5. Here, Q is equal to M dot 6 is just the M dot, H6, M dot 4 is Y, M dot H4, M5 is 1 minus Y, M dot H5. So this is the heat flow that is leaving the compressor, and this is the equation you would use to solve it using the mass control volume. Alright, what is left? We have the pump. One pump. Basic work equation, work is equal to m dot inlet minus outlet. Boiler, one inlet, one outlet. Q hot is equal to m dot H1 minus H8, exit minus inlet. Now, like I said, boiler, the amount of heat you have to put into, you can even mathematically do this out. Ignore 8 and ignore 3 and 4. Just see how much, if you were to go straight from state point 1 to state point 5 here and removing the closed feed water heater, you can see just how much extra energy you have to put into your boiler to pump up, to heat up the water to the new pressure. With this closed feed water heater, you're reducing the amount of heat you have to pump in through the boiler. You're going to make, that way you're reducing the heat input while getting more work, getting the same work out. So you're going to increase your efficiency. So efficiency is equal to work net over Q high. Reiterate, without the closed water heater, Q high would be a lot higher because you have to go from 7 to 1 instead of from 8 to 1, where 8 is preheated and has a higher enthalpy than 7. So the enthalpy difference between 1 and 8 will be a lot less. Therefore, you will have a more efficient turbine power plant. So this is equal to work of high pressure turbine plus work of low pressure turbine minus absolute value of work of pump 1 minus absolute value of work pump 2 all over the input heat from the boiler. So let's reiterate. You can go through this stuff to go over the math of it, but we're going to go over the quick concepts of it. Water flows from the boiler into the high pressure turbine. Some of that, or steam flows. Some of that steam is siphoned off after going through my high pressure turbine, some Y amount. The rest of it, 1 minus Y, is sent here into my low pressure turbine. That steam then goes to my condenser Meanwhile, the steam that was siphoned off my high pressure turbine goes into a closed feed water heater where it preheats the water that's going to go into the boiler and then flows off to rejoin the rest of the steam in the condenser. The liquid then goes through the pump, preheated by the closed feed water heater, and then into the boiler. Cycle rinses and repeats. Here's a TS diagram. Remember, regardless of how I drew it, T8 is always less than or equal to T3 because if I'm putting in steam, the water cannot heat up more than the steam. It's not possible. And then this is the math behind it. And then here's the efficiency. This will, after the next couple cycles, or the next episode, I will show you how to do a reheating problem, what that does to the efficiency of your power plant, and how it can help or hurt you. Thank you very much and have a wonderful night.